question number 3, an 80-kilogram man is standing in an elevator on a bathroom scale, of course. The bathroom scale is calibrated in kilograms, and that's kind of important because even though he might have a certain weight, the bathroom scale is calibrated. It's on the earth, and it's designed to convert that measurement into kilograms. So if we just do a sort of quick calculation before we start this problem, if we calculate his FG, this is 80 times 9.8, right? So that works out to 784 newtons. 784 newtons. So that's what the scale would read, 784. But it's smart enough to have a conversion, so it's converting that back to 80 kilograms. But what it's still measuring, the scale reading, as we talked about in the previous question, the scale reading is always, READ, is always talking about force, normal force. In this case, since we want it in kilograms, we're going to take the normal force and divide it by 9.8, or by G, I guess you could say, if you want to be more formal about it, by G. Okay? So what are the forces acting on the person? Well, the same forces as always. There's a force of gravity acting down, and then there's the normal force acting up. If this elevator was at rest anywhere, or if the elevator was traveling at a constant velocity, those forces would be balanced because A would be 0. So Newton's first law would kick in. Fn would equal Fg, and the scale would read 784 newtons. But this scale is not moving at a constant velocity. It's accelerating downward at 3 meters per second squared. So 3 meters per second squared. So if you think about it, if it's accelerating down, that means the net force in the downward direction should be greater than the normal force. Well, Fg doesn't change. It's always 784. What changes is that Fn is going to be slightly different. By how much? That's what we have to calculate. So looking at this in the vertical direction, we can do our MA equals the sum of the forces. Now, we're going to be sort of intentional and very careful about how we choose our sign convention here. Normally, we make down negative, up positive. But in this particular example, our acceleration is down. So you have two choices. You could make down negative, but don't forget to make your A negative. Or you can just take that worry out and make the direction it's accelerating positive. And therefore, we get MA, A now is positive 3, equals, and since Fg is in the positive direction, it's Fg minus Fn. Okay? And then when we rearrange this, so remember, whenever you're solving for apparent weight, you're always trying to solve for Fn. So in this case, we're going to solve for Fn. Fn equals Fg minus Ma. Did I do that right? Yep. And then this equals Mg minus Ma. And we can plug the numbers we know in. 80 times 9.8 minus 80 times 3. And that gives me, so 80 times 9.8 minus 80 times 3 equals, I can't see my calculator, it is 5.44, I think. Or sorry, 544 newtons. 544 newtons. So you can see the normal force is not equal to the force of gravity. It's smaller than. So then how do we get this? So now the question asks us for scale reading. The way you find scale reading in kilograms, it's like the scale thinks that 544 newtons are being pressed on it. I mean, your scale doesn't know. It thinks it's in your bathroom. It thinks it's sitting in your bathroom at rest and there's a 544 newton person standing on it. It doesn't know it's actually in an elevator accelerating down so that the normal force is smaller so that there's a 784 newton person pushing down on it, but it's accelerating, therefore the force it feels is less. What it thinks it feels is the normal force divided by G, which is 544 divided by 9.8, and we get 3 55.5 kilograms, or 56 kilograms. So to be clear, this is what the scale, this is obviously not true, right? This person's mass has not changed from 80 to 56, but what the bathroom scale thinks, this is what the bathroom scale thinks. And not only is it what the bathroom scale thinks, but it's also how you feel, how he feels. He feels lighter because his normal force is smaller. If you're on a roller coaster and your normal force decreases, you feel lighter, and that gives you a sensation of, it gives you that bottoming out of your stomach feeling. So all it's doing is playing with your normal force, nothing else. Your force of gravity never changes.